And I am live. That is pretty cool. And today is 29th of September 2025, Monday. And we will now begin solving, not solving, but getting into graph theory and getting more familiar with how graphs work and what graphs are, trees, DAG. DAG is just directed acyclic graph, DAG. And that is a pretty nice intro. And I'm not in the middle of the screen. Yes, now shit. Okay, cool. Right, fine. And our source material is going to be Competitive Programmer's Handbook, of course. Like, yes, stop this and cool. Yeah, Competitive Programmer's Handbook, and we are going to go through. And yes, I do have a plan. This is graphs. This is the first chapter in the graph section, terminology and representation. Then there is traversal methods in graph. And for today, the goal is going to be to go through these two chapters, these first two chapters, terminology and representation, and then graph traversal methods, and also do some CSES questions on graphs. I have already done some questions, so I will just, first of all, I will do all of these questions again and maybe get this one also right. I got this wrong last time I did this. So that would be the goal for today's video, these two chapters and those CSES questions. And then in the upcoming streams, there is going to be shortest path, and there are three algorithms for shortest path here. And what I do know about them is Dijkstra algorithm is to get the shortest path when our source is fixed, and Floyd-Warshall algorithm is when our source and destination both are dynamic. They can be anything, and this algorithm gives us the shortest path between any two pairs. And Bellman-Ford, I don't know. And tree algorithms, yes, this is something that we will have to go through. Like, of course, we do encounter trees, so that would be nice. And spanning trees, that will be cool to know about. Directed graphs and topological sort is something that I really want to get into, what that is and how it actually works. And then dynamic programming in directed graphs is going to be pretty cool. Counting the number of paths and then extending Dijkstra's algorithm, representing problems as a graph, which is the same as which is which is a mathematical concept in which when you have a problem and it is hard to solve that problem as it is, so you propose another problem and you say that these two problems are equivalent, and if you find solution to this new problem, you will also find solution to the original problem, so you proceed to solve this new problem, which is easier to represent. And that is what this means. You can represent some problems as graphs and then proceed to solve them as if they were graph problems. And there is a term for this, and that is isomorphism. Those two problems which you can interrelate or equate as being equivalent, those two problems are called isomorphic. And yep, tree algorithms, then spanning trees, then directed graphs, strong connectivity, no idea. Tree queries, that is going to be cool. Path and circuits. Path, we do know. Circuits, maybe closed paths. And then flows and cuts. That is going to be the last thing. So for today, these two things, terminology and representation, and then traversal methods, and then CSES questions. Let's begin. That is nice. Basics of graphs. And this just says graphs. And also, at some point, we might use CLRS because there is a lot of graph material in CLRS. Graph algorithms. There is elementary graph algorithms. All of these are elementary. Topological sort is also supposed to be elementary here. Minimum spanning tree, single source, shortest path, Bellman-Ford, Dijkstra. These two are single source, shortest path, and all pair shortest paths. Here we have Floyd-Warshall. Okay, then we have maximum flow, and then matching in bipartite graphs. This is like pretty cool. I think there is also advanced section. No, there is no advanced graph algorithms here. Yeah, but there is a advanced graphs questions section in CSES. String algorithms, geometry, advanced techniques, sliding window problems, bitwise operations, constructive construction problems, and yep, advanced graph problems. And that is nice. These are pretty hard. Only 58 people have been able to solve this, split into two parts. That is crazy. All right, graph terminology, basics of graphs. That is going to be the first thing. And we are going to attack this the same way we did with dynamic programming. And yes, I also have a nice extension, CP handbook, which would be very handy right now. And that is this one, black PDF, black and white PDF, basics of graphs. Cool. Basics of graphs. Many programming problems can be solved by modeling the problem as a graph problem. That is mathematical isomorphism, and using an appropriate graph algorithm. Okay, a typical example of a graph problem is a network of roads and cities in a country. Sometimes, though, the graph is hidden in the problem and it may be difficult to detect. So, this whole paragraph makes sense. Sometimes we can convert some problems into graph problems and then apply algorithms which we already know for graphs to solve those problems. That is nice, and sometimes it is like very easy to see when a graph can be used in a problem, and sometimes it is not very easy. This part of the group of the book discusses graph algorithms, especially focusing on topics that are important in competitive programming. In this chapter, we go through concepts related to graphs and study different ways to represent graphs and algorithms. Okay, we will see some concepts related to graphs and how we represent graphs in algorithms. And how we represent graphs in algorithms is actually pretty cool. Like very important thing, very basic, but also it is very important. Graph terminology. Yes, that is also very important. A graph consists of nodes and edges. Makes sense. We have nodes and we have edges. In this book, the variable n denotes, in this whole book, not just this chapter, but the whole book, the variable n denotes the number of nodes in the graph, and the variable m denotes the number of edges. Makes sense. The nodes are numbered using 1 to n, 1 indexed. For example, the following graph consists of 5 nodes, as we can see, and 7 edges. 1, 2, 1, 2, 3, 4, 5, 6, 7. Cool. A path leads from node A to B through edges of the graph. Yes, a path leads from node A to B through edges of a graph. The length of a path is the number of edges in it. For example, the above graph contains a path. This is a path, and there must also be a representation for path. And to represent a path, we can just use a vector in which, since a path from a node A to B consists of edges, we can represent those edges as connections between nodes. When we are going from 1 to 3, we can say first we were at 1, then we went to 3, then we went to 4, then we went to 5. And we can store these numbers in a vector, and that would be our representation for a path. And that makes sense. That is like true. A path is a cycle if the first and the last node is the same. Okay, and it is also a path For example, the above graph contains a cycle 1, 3, 4, 1, 1, 3, 4, and then 1. That is a cycle. A path is simple if each node appears at most once in the path. So, okay, every path is a every cycle is a path, but every path is not a cycle, like alkaline and basis thing. And yes, a simple path is a path where each node that is a part of the path only appears once. If each node appears at most once, which means they can appear or not appear, but when they do appear, they should not appear more than once. Hello. Have you no CL? No, I haven't completed CLRS. There is just a lot of stuff in CLRS. There is like in the later chapters, there is FFT, fast Fourier transformation, and NP completeness, and B trees, augmented data structures, parallel algorithms. I think this is shit. I think this parallel algorithm sections is when your computer has multiple things, multiple cores where you can do stuff. Yesterday I was reading C++ book, but I didn't like that. Too deep and boring, and I cannot read that shit. Yes, I also felt the same thing when I was reading it the first time, and yes, it is too deep and it is boring. It feels almost like torture, but if you do read it, then you will become a giga chad. You will have like a lot of insight, knowledge of how things are, and because of that book, the way that I write programs is now like uh, you might see that in that book, variable names are not big. Variable names are like just a single character A, B, and something like auto B equals IT dot begin or something like that. Variable names are just a single character, and that is why how my writing style is like that, because all my C++ that I've read besides me is from the book. So I started CLRS and I liked that book. It is not that boring and I think I can read it. Yes, you can read CLRS. It is also pretty amazing. I think I should read it and won't recommend to anyone as well. Okay, if you don't want to read, you don't have to read. And yeah, it is like up to you. But I would say if you okay, I guess we have different philosophies which relate to this. I think that if I want to become a good programmer or I want to become someone who I can call a good programmer, then that good programmer should be able to read that book. And that is why I force myself to do these things. And yeah, that is just my philosophy. Yep. CLRS is pretty cool. If you go through, I think it is better to learn C++ from tutorials and online. Yes, the point is that you are just learning C++. The resource does not matter, right? And also CLRS book. In the CLRS book, if you go to the first few chapters, I think in one of these chapters, they introduce a topic called loop invariance. And that is like very important. If you understand what loop invariance is, then it will become very easy for you to write algorithms. You will be able to determine what things are true before you enter a loop, and while your loop is executing in each iteration, those things should remain true, and when you exit the loop, those things should also remain true when you terminate the loop. And if you know those things which are invariant, which do not change when you exit the loop, then you will be able to expect what the state of your program should be when you exit the loop, and you will be able to yo hello And if you know what the loop invariance is, then you will be able to predict, or yeah, predict what the state of your program is going to be when you exit, and it is pretty cool. You will be able to handle that state. And I have to turn on the fan. Light is gone. My bad. And loop invariance is one of the crazy things. It is very simple and it just helps in a lot of things. Uh, in CLRS, think, well, I went through the dynamic programming section on stream, and of these chapters, but not like with complete guns blazing focus, but yes, I've gone through these chapters and heap sort, quick sort. Okay, with heap sort and quick sort, I'm not very confident. I read them like few months ago, more than a few months ago. And yes, elementary data structures, hash tables, binary search trees, and red-black trees. I have done till insertion and not deletion. Insertion was fine, but deletion, I left at deletion and I didn't read about deletion, how to do deletion in red-black trees. And here dynamic programming, and that is it. The next thing is just graphs. And there are a few things about graph. And yes, Eric, I have a like really nice thing. Computational geometry, this one. Yes, computational geometry. You said that you were getting into computational geometry. I think this is a classic book for computational geometry, just like CLRS is for algorithms. And yes, the algorithms and applications, like literal applications and algorithms. So yeah, when I will be doing computational geometry, I will be reading this book. And that is pretty nice. The prerequisites are not much. No knowledge of the application domain is required, and hardly any knowledge of geometry is required. You can just begin solving this book. So that is going to be nice. There is convex hulls, binary space partitions, robot motion planning, shit, visibility graphs, simple range search. I don't know what robot motion planning is. Getting where you want to be. Agent, the painter's algorithm, mixing things, windowing, Delaunay triangulations, arrangements and duality, Voronoi diagrams. Yeah, it is going to be fun. Orthogonal range searches, orthogonal is, I think, uh, like perpendicular. I think orthogonal is perpendicular. Yeah, so it is going to be fun when we go through that. Geometry, but it is easier to visualize, right? And graphs, CLRS, oh, not CLRS, not yet, but handbook, CP handbook, competitive programming handbook. And also one more thing, I just saw this. There is the command grep, right? I think I have ELDR, grep. And do you know why grep is called grep? In Vim, there is a command called global, and this is the syntax for this command, global command, and it is range. You apply a range, and then the G command, global command, which you can just represent using a G, then a slash, then a pattern, it would mean, and then the command. And what this does is, in this range of lines, this global command will find all the lines which specify this pattern and execute this command on all the lines which have this pattern. And you can, if you want, write this as this. Here, this G is for global, RE for regular expression, and P is the print command, which is the default global command, which you can see. Default is P right here. And this is just grep grep. That is why that is the epistemology or epistemology of grep. And that is just pretty cool. That is why grep is called grep. Yo, hello. And now getting back to graphs. Yeah, grep is nice. Grep is pretty cool. Grep is now a verb, not just a noun. It is a verb now. Does SQL also have grep command? I think I have. This is a Linux command, not about sed. What is sed? Uh, sed stream editor. A sed utility reads the specified files or the standard input if no files are selected, modifying the input as is specified by a list of commands. Okay, the input stream is then written to the standard output. Okay, so sed takes in something. Sed is just stream editor. It takes in some text either from a standard input or from a file. If a file is not given, then it takes into standard input and we can redirect it or pipeline it into a file. A single command may be specified as the first argument to sed. Okay, and it takes commands as arguments like sort. Multiple commands may be specified by using E or FE. And also shit. Since this man page for commands is not very user friendly, we have TLDR sed, and this replace all Apple basic regex. Execute the sed command. This is the command. Substitute Apple with Mango. Wait, this is taking in a Linux Vim command. This is a Vim command. And if I write uh, echo Apple Apple into hello.txt and then sed and the sed and then substitute Apple with Mango on the whole line and file is hello.txt. Shit, no such file or directory. Mango. Okay, I have to give a command here. Hmm. Hmm. Sed script cat hello.txt sed s apple mango. Okay, and if I now it is working. So this cat hello.txt takes all the text from hello.txt and gives that text to the sed command, and sed command executes this command on the file. And since I didn't say that you have to put this back to somewhere, then the output of the sed command went to standard output and we have mango here. But if I were to redirect this back into hello.txt, and now if I cat hello.txt, shit, it is empty. Hello.txt is empty. It is literally empty. Okay, so something went wrong. It is empty. Grep search for text patterns in file. Yes, and grep is very powerful. Right now, why is your username? That is a crazy username. Right now, the rating is 1396. Almost there, almost, but very far away from 2000 still. And yes, getting back to studying connectivity. So we have seen nodes, paths. In a graph, we have nodes, edges, and we have a path. And a path can be a cycle, and a path can be a simple path or not so simple path. And then connectivity. A graph is connected if there is a path between any two nodes. For example, the following graph is connected. Yep. And the graph is not connected because this graph is not connected because there is no way to get to node 4 from, let's say, node 1. The connected parts of a graph are all called, and this is one of the important terms, components. This whole thing is a graph of 8 nodes, but this graph has 3 components. One is this component which has nodes 1 to 3, another is this component with nodes 4, 5, 6, 7, and another is the third last component is this with only a single node 8. And these are called components because they are not connected to each other. A tree is a connected, where you can go to any other node from a given node, connected graph that consists of n nodes and n minus 1 edges, and that is the basic property for a tree. There is a unique path between any two nodes of a tree. For example, the following graph is a tree, and tree is pretty cool. Tree is first of all a connected graph, and the number of edges is 1 minus the number of nodes. And for every pair of nodes have a simple path which connects them, and that simple path is unique for every pair of nodes, and that is simple. That is like pretty cool. And also, if you were to add a singular edge, then this tree will become a cycle. And if you were to remove any edge from wherever, from any place in the tree, then this tree would have two components, and that is crazy, kind of. Edge directions. A graph is directed if the edges can be traversed in one direction only. Yes, for example, the following graph is directed if these edges have like direction to them, that is, one node is the source and the other is the target, then this model of graphs is said to be directed. In the above graph contains a path 3 to 1 to 2 to 5. 3 to 1 to 2 to 5. That is one path from node 3 to 5, but there is no path from node 5 to node 3, from node 5 to node 3, because node 3 is not the source. There is no way we can go from node 5 to node 3, even though they seem to be connected, but the direction of these edges is like stopping us from going to 3 from 5. Edge weights. In a weighted graph, each edge is assigned a weight, and these are just different models. Till now we have seen there is the basic graph with and some terms for the graph, edges, nodes, and everything. And then what is connectivity, what are components, and then there is a special type of basic graph called tree, which has n minus 1 number of edges, and it is a connected graph. And then there is another model of representing a graph in which these edges might have directions, and then there is another model of a graph in which edges have weight, and nodes might also have weight in some representations. Thank you to persevere for a long time. This is just the beginning. This is just the beginning. I'm going to be here. You have already read all of these material, it seems. I have only read these two chapters for graphs, basics, and the next chapter, basic graph traversal. And yes, that is it. Those edges are called bridges, and vertices are called vertices. Are that is informational. Bridges, bridges. Okay, that is nice. Bridges. How do you find the motivation to do this for 199 days in a row? Not exactly 199 days in a row. Uh, I started streaming for the first time last year, and then I stopped, and then I started no, I started streaming. Yes, for the first time last year, for the first time in January this year, and then I stopped in the middle, and then I started streaming again in June, and then I stopped in the middle for a few days, and now I have been at it since then. And yeah, internal dialogues, bridges. That is nice, bridges. By the end of this year, and there are 3 months left, and I think I will make it. Edges weight in a weighted graph, each edge. And yes, to just recap again, even though we have just gone through 2 pages, first we have seen some terminology, and then there is the basic graph model, and then there is another model for edges in which edges are directed, and then there is weighted model, and these two models could be connected. Like VR graph could be directed and also have edge weights. And that is crazy. In a weighted graph, each edge is assigned a weight. Uh-huh. The weights are often interpreted edges as edge lengths. Okay, weights are often interpreted as edge lengths. Makes sense because weights are just a number. What do you mean by weights? They do not have any physical weight. So we interpret those weights as edges. That is a mental model we can use to think of them. Even though here uh, this edge 5 seems to be longer than this edge 7, so not to scale. For example, the following graph is weighted. This one. The length of a path in a weighted graph is the sum of the edges. That is why it makes sense to interpret these numbers as lengths of the path. Makes sense. For example, in the above graph, the length of the path 1 to 2 to 5 is 1, 1 to 2 to 5 is 5 plus 7, that is 12. And the length of the path from 1 to 3 to 5, 1 to 3 to 4 to 5, 1 to 3, 1 to 3 to 4 to 5 is 1 plus 7 plus 3, 11. The later path is the shortest path from 1 to 5. Even though this one has more edges, this one is the shortest path from 1 to 5. Yes, so we cannot use greedy here, greedy algorithm, looking for the shortest path by just seeing the fewest number of edges. That is bad. Neighbors and degrees. Yes, that is also important. Degrees is a nice word. Two nodes are nodes, vertices. Nodes are neighbors or adjacent if there is an edge between them. Neighbors, adjacent. I haven't used this term, neighbors and adjacent. I guess, yeah, this might be more useful, I guess, later. Yeah, but till now I haven't had the opportunity to use these two terms, but I have had the opportunity to engage with the term degree. The degree of a node is the number of its neighbors. Makes sense, number of its neighbors. Even though if a node is connected to itself, then is it its degree? No, it will not increase the degree of the node if there is a self loop on a node, because degree of a node is the number of its neighbors. and a node is not its own neighbor, right? Yes, I am in college. I am a newbie. I can reach. Yes, if you want to, you can. What do you think about the state of competitive programming considering AI's rapid improvement? Uh, It is for the good. You can use AI to learn things. So that is shit. These guys greedy. Shit. So there is a lot to learn, I guess. Third, I'm in my third year, supposed to be in my third year, yes. But I don't go to college. College is bad. Do not go to college. These guys, by the way, pretty cool. It is greedy. That is XD. And shit, I realized only a few days ago that this XD is supposed to be like emoji who is squinching one of his eyes and laughing with mouth open, and that is like crazy. This thing, like a guy who is squinching his eyes and laughing at the same time. That is crazy. I meant 18 by the end of this year. Also, I joined your Discord server. Is your name? Yes, that is my name. Yes, you will be. Wait, I did something right now. Yes, you will be able to get to LOL. I'm only in HS. What is HS? Yes, you will be able to reach 1800 by the end of this year, depending on how much effort you are putting in, and 3 months. And you are currently a newbie. This is difficult. This is difficult because I have been doing this at this point for 3 months and I am almost at 1400. Ah, high school. Shit. Makes sense. He's high schooling. Okay, shit. Shit. That is okay. Yes, of course, it is high school. And yes, I have been at this for 3 months and I am almost at 14. So 1800 by the end of this year is hard, but the point is, if you do give your best, you will at least reach 1400, which I am able to reach, or maybe you will reach higher. But yeah, you can do pretty good. At least you will be better than you are right now to CP. But yeah, my ad hoc is shit, so that's why rating is so low. So yeah, if the main point is that you will improve, right? So just focus. And for me also, getting a higher rating is not the main thing, even though I use a clickbait type title, reaching 2000. That is not the main thing. The main thing is this learning, right? By the end of this year, even if I'm not at a rating of 2000, I will be much better off than I was when I started this so-called challenge. That is the main thing, right? Yeah. And for the next year, I have like a lot of plans. Since my C++ would be really good by the end of this year, the next year there is build your own X, and I have chosen a project, and that is this one. Build your own Redis in C++ from scratch, and this is going to be very cool. We will be implementing socket programming, TCP servers, clients, request response protocols, concurrent models. This is going to be very cool. Concurrent models, when like different clients are trying to talk to your server and you are talking to everyone at the same time. Key value server. This is going to be pretty cool. Event loop part 1, part 2. And this all will be in C++. So we will not be abstracted from the basic things, and we will know from bottom up. Our knowledge will be like, we will become really strong. And as Richard Feynman said, what I cannot create, I do not understand. That is why he used to teach. Nope, nope. No, I just started like 3 months ago, C competitive programming. And this is pretty cool. Richard Feynman was a pretty nice guy. He also has a book on computation. many lectures on computation. This book, and this is pretty nice. And in the first chapter of this book, he explains about a what essentially a computer is doing, and he also has a lecture on that same chapter, and that is 10 lectures on computation. Yep, this is the video, and this is also pretty nice, really cool video. He explains about what computers are and what they do, and yeah, it is pretty cool the way he explains and shit. Hello, you could belongs to regionals next. Probably. Okay, yes, I will do. I will do regionals next year if I am pretty good. I think I will become good if I just continue, and I'll do regionals next year. Let's meet at the regionals. If I manage to get there, we might be able to meet actually at the regionals. Is it CP? Yep, it is. 3 months. Yeah, it is cumulative. How did you read so many books and videos in such a short time? No, I all my competitive programming knowledge came in the last 3 months, but other things I've been reading books for since Corona. But I was very stupid and retard, but now it is much better. Go at some of the SPPC regionals. SPPC. And yes, one thing which I can say is going to be very beneficial for you also. It is, since we all are humans, we can agree on that fact. We are inherently RIOUS. I hope that spelling is correct. We are inherently curious, so we can use our curiosity for our benefit, right? Instead of thinking about looking at a concept and thinking, oh, I should get this concept because I will be needing this or something. You can just become inherently curious about that thing. Think of yourself as a, if you are reading about biology, think of yourself as a biologist. If you are reading about anything, think of yourself as a professional in that field, and then be curious, and it will make more sense. Good morning, you are typing with your Kinesis Advantage 360 keyboard. CP 1396 at this point, and shit, SPPC. I got distracted. South Pacific Competitive Programming Association. I am I a part of South Pacific? No. So what? Southwest Pacific in India has a strong economic and strategic ties with the South Pacific. Okay, so we are very good friends, but we are not the same. No. Okay, you said yes. Good morning. Oh, okay, you won't be there. Shit, that is fine. Okay, that is okay. 360 Pro wireless gray colored with, okay, bro is just flexing at this point, but let me keep a note. I will take a screenshot so that I remember all these details. 360 Pro wireless gray colored with brown switches. Brown switches? Nah, nah. Brown switches, no. This is bad. Brown switches, no. You should have had red switches. Brown, no. Bad. I just need VPN. The ICPC regions for US is ANZ region. What is ANZ region? I just need VPN for, I think we have to go physically there to participate, not VPN. Been to ICPC regions twice. That is pretty cool. And are you from India? They're right. I think you are from India, like how you went to Greenland in CA. That you can just, since my supposed name is Walrus, you can go to your settings and change your country to anything you want. And there are actually, I'm the third person, like top three in Greenland. Here, I'm top three in Greenland. And that is pretty cool. Dope. Go to their website. Look. Okay, let me see. Oh, me too. The only truth. My bad. Shit. Should I start CP or stick to DSA only? I look at them as the same thing. So, like, what is the point if you are only doing DSA? Do CP, that is better. And I'm also in my fifth semester. So, do CP, competitive programming. You are from India. So, what is like ICPC for India called? For us, Australia, it is called South Asia Pacific. What is it for India? Okay, cool. Shit. No, I'm in India. Sure. And both the same? Yes, they are both the same. Not technically, but yeah, spiritually, they are the same thing. And you should do competitive programming. And let me look up the website, not brown switches. Kinesis advantage. Yes, I got this. Yes, it looks pretty cool. Just looks cool. And your this thumb thing. What was the term that you used for thumb thing? Like the thumb when you can use the thumb for writing. Third tier, like the worst college. Thumb cluster, thumb cluster, thumb cluster, thumb cluster, and pinky twist, something. Uh, Pinky column. Do live practice for CB to show how one should practice for CB in 12 hours live stream. Yes, I am planning to do that in a few months when it is cold. Less use, yes, less use of pinky finger. But I think you used a specific term for that thing, like thumb cluster, the thumb cluster. I am stuck on pupil ratings for so long and cannot improve. On my new account, I got a specialist rank. Shit. Uh, but after that, I am not giving contest on the new account and start giving contest from old account. So if you are unable to grow and you are stuck at a rating, it is like it is an indication, I would say, that you are not studying much and you should study more. That is what I would do if I was stuck, which I feel like I am stuck. Wait, where are graphs? Study more. I find like in DSA, we just learn and implement code in textbook style, while in CP it is dynamic and combination of many things. Yes, if you are going to do DSA, if you have a choice between DSA and C and competitive programming, you should go with competitive programming. This is Competitive Programmer's Handbook by Antti Laksonen from Helsinki. This is a draft. And yes, this one is for free on the web, but there is another one which is more comprehensive than this one, which is this one, Guide to Competitive Programming by Antti Laksonen, the same person, Antti Laksonen. I think that is why this is a draft, and this one also came out in 2018, and this one came out. the 2024. This one came out in 2024, and this one also has 2024. Helsinki, Finland, Anti-Laxonen, April 2024. And this one also has some things on Python: efficiency, sorting, data structures, dynamic programming, tree algorithm, mathematics, advanced graph algorithms, geometry, string, additional topics, Python, and competitive programming, and preparing for IOI. This is the new section which is not there in this book. And future of competitive programming with generative AI. What will happen next? Now we are going to philosophy at the end of this book. That is nice. Yes, that is why I do not read from this book, and I read from this book. For how long? You doing 3 months at this point, about 3 months. And let's get at this. And how long? It's been 51 minutes. Shit. Okay. Graph terminology, edit distance, edit edge weights, not edit distance. It was edge direction, edge weights, neighbors and degrees. We know about what neighbors and what neighbors are, what is a degree. For example, in the following graph, this one, the neighbor of node 2 are 1, 4, and 5. So its degree is 3. 1, 2, 3. Yes. The sum of degrees in a graph is always 2m, twice the number of edges, because whenever you have one edge is connected to two nodes, and that edge, that every singular edge will be counted as a degree twice by both of those nodes. Therefore, 2m, where m is the number of edges because of each edge increases the degree of exactly two nodes by 1. Yeah. M nodes increase the degree one time for two nodes. They do this m times, so 2m. By this reason, the sum of the degree is always even. That is also true. A graph is regular if the degree of every node is a constant. Okay. A graph is complete if the degree of every node is n minus 1. That would be when every node is connected to every other node. That is, the graph contains all possible edges between the nodes. Okay, complete makes sense, but regular, I think that is the reason why we have regular polygons, right? Because if we think of this as a graph, each vertex has the same degree, which is 2. If that is true, then be curious, yes. If that is true, like the reason that these things are called regular is because each node has the same degree, which in this case is 2. Then, shit, that is too big. Then if we have a figure like this should also be regular, and we can confirm our doubts from ChatGPT. uh, Called regular if the degree of all of its vertices is same, and generally uh, degree is 2. But can we have regular polygons with higher than 2 degree? Can we have that? No or yes? Let's careful. Okay, I guess I mongled up two things, geometry and graph theory. Untangle this because there are two different languages overlapping makes sense. polygons and graph theory. In geometry, a regular polygon is defined as a convex, and there is a very good definition for what convex shape is, or a star shaped. Star is not convex. Star is not a convex. All sides have equal length and all interior angles are equal. Okay, yeah, I messed up the definition. Regular polygon and regular graphs. Here, the notion of degree of a vertex doesn't even show up. Instead, okay, so we have the same word regular in geometry and in graph theory, but with different definitions. So, okay. But a star is not a convex. The definition of convex that I have heard is that if you have a shape, any shape, and it is convex, is if it is only convex if you have a line, you cut the shape in two, and the number, let me get it right, yes, the number of regions, new regions, is going to be twice two. The number of new regions that are formed is going to be two. Like in this case, this shape is convex because when we cut this like this, the number of regions is two, and there is no way to cut this shape in a way that the number of new regions formed is going to be greater than two. But if we have a shape like this and we cut this like this, here the number of regions is 1, 2, and 3. So this shape is not convex. NC complete. Yes, a little pun there. So yeah, that is this is concave because when we cut it, there are more than two regions, and this is convex because when we cut it, there are exactly two new regions formed. That is pretty nice. Not right now. Right now we have to go through graphs. What do you think if someone doesn't know about a topic? Should he skim through CLRS and then read CP handbook, or straight read CP handbook? Like I generally switch. I read about dynamic programming first from CP handbook, then again CP handbook, and then from CLRS, and then from CLRS again, like twice each time from both the sources. And there was also this thing, CP algorithms for competitive programming. Yes, you can switch. There is like you don't have to stick with anything. There are also YouTube videos on dynamic programming. Amazing 3 videos by Ericto, and those are nice videos. Okay, we know about neighbors and edges, about regular graphs and complete graphs. Complete graphs have every node is connected to every other node, and in regular graphs, the degree of each node is same. In a directed graph, the in degree of a node, okay, in degree of a node is the number of edges that end at the node, okay, in a directed graph. And the out degree is the number of nodes that go out. That is for how many edges is this current node the source, and for in degree, for how many edges is the current node target. Okay, for example, in the following graph, the in degree of a node is 2, of node 2 is 2, and the out degree is 1, and the out degree of node 2 is 1. Okay, coloring. Yes, that is one of the things. Coloring in a graph, in a coloring of a graph, each node is assigned a color so that no adjacent nodes have the same color. Okay, okay, let's let him cook. A graph is bipartite if, okay, coloring. Okay, this is the one problem I would say I have with this book. It is that here The book says, Mr. Anti-Laksonen says, the coloring of a graph, each node is assigned a color so that no adjacent nodes have the same color. Right? That is what they are saying is the definition for coloring. But I think that is the definition for coloring can be anything which you want, but generally, this is what someone wants when they say someone means when they say coloring of a graph. This is not the definition of coloring. This is one of the definitions of coloring. This is a definition of coloring, not the definition of coloring. And that is the problem I have with this book. But if I were to read from the CLR's book, I suppose I would see that this is one definition and not the definition for coloring. Okay, this is red black trees. Graph coloring problems. Hungarian graph coloring. Okay, let's see. Map makers try to use as few colors as possible when coloring countries on a map subjected to. Okay, I'm not Bonnie blue. Map makers try to use as few colors as possible when coloring countries on a map, subject to the restriction that if two countries share a border, they must have different colors. You can model this problem with a undirected graph in which each vertex represents country and vertices whose respective countries share a border are adjacent. Like, this is a much more comprehensive definition for coloring. And they begin with the example, and then they say that we can model this example on a graph, on a simple undirected graph, where each vertex represents a country and a edge represents a border. Vertices whose respective countries share a border are adjacent. Then a key coloring is a function C, which takes in the vertices and gives numbers 1 to k such that Cu is not equal to Cv for every edge. Okay, the color of the vertex U is not equal to the color of vertex V if vertex U and V are connected to each other, which is exactly the same thing that they have said here. But here, they this is more like a dictionary definition, and this is more like a epistemology. Etymology. This is more like a etymological definition of the word. Why we need to have adjacent nodes with different colors. So that makes much more sense. Why adjacent nodes should have different colors. The graph coloring problem is to determine the minimum number of colors needed to color a graph. And this is just amazing. This definition for graph coloring is amazing. And you cannot blame Mr. N.T. Laksonen because he only had 296 pages to write this book. And also, he cannot, like, this is free. He is making this available for free. So we cannot blame him for this. And this is a much more comprehensive definition. We now know why we want to color the graph with as few colors as possible, and also why two adjacent vertices should have different colors because they are more applicable in a scenario like this when we are using that graph to model countries. A graph is bipartite if it is possible to color it using two colors. Okay, that is a good definition of bipartite. It turns out that a graph is bipartite exactly when it does not contain a cycle with an odd number of edges. For example, the graph this. contains a cycle. And what? It turns out that a graph is bipartite exactly when it does not contain a cycle. It does not contain a cycle with a odd number of edges. Here there is a cycle, but the number of edges in the cycle is even. But if the number of edges in a cycle were to be odd, then no bipartite graph. Okay, we have a bipartite graph only when we have a cycle, but the number of edges in that cycle is even, or the number of nodes involved in that cycle is even. That does make intuitive sense. Here we have this bigger cycle, 1, 2, 3, 6, 5, but and also this is smaller cycle, 1, 2, 5, but the number of nodes is even. So if we were to say color this node in red, this one in blue, then this one would have to be red, and now this is connected to this, so this would have to be blue, this one would have to be red, this one would have to be blue. So that is like super state quantum mechanics thing, and therefore this graph is not bipartite. Yes, this is not bipartite because it is not possible to color the following cycle of 3 nodes using 2 colors. Yep, because even, because odd, number is odd, number of nodes involved is odd. Simplicity. A graph is simple if no edges start and end at the same node, like this cycle, and there are no multiple edges between 2 nodes, like this. Often we assume that graphs are simple. For example, the following graph is not simple because we have a self loop and we have stuff like this going on, crazy stuff. And now the representation of graphs. And there are 3 main representation of graphs, and that is pretty cool. There are several ways to represent a graph. We are going to read about 3. The choice of a data structure depends on the size of the graph and the way the algorithm processes it. Yes, since there are multiple ways, then the data structure that we are going to use to represent a graph depends on what we want to get from our graph, the way the algorithm processes it. Okay, what are the operations that we need to get from the graph? If we only need to know the degrees of nodes, then a simple array would suffice, in which the ith index would represent the ith vertex and the value would be the degree of that node. And if we need some more complicated algorithm to run on it, then we would need some more complicated or different data structure. Adjacency list representation, this is the most common one which we use. In the adjacency list representation, each node X in the graph is assigned an adjacency list. Each node has a list of its own that consists of nodes to which there is an edge from X. So each node has a list associated with it. That is, he is here Jakob Steiner. Each node, um, yep, let's say we have 1, 2, 3, 4 nodes, each node, and our graph looks like this: 2, 3, 4, and these are connected like this, let's say, and each node has a vertex or a list, or yeah, not a vertex, a list or a vector, we could say anything, assigned to it, and this vector will have all the nodes which are connected to one. So 2 is connected to 1 and 4 is connected to 1. So this would have 1 and 4. This would have 2 and 4. And 2 is connected to 1 and 3. So this will have 1 and 3. And 3 is connected to 2 and 4. So 3 would have 2 and 4. And this looks like a B3. And 4 is connected to 1 and 3. 1 and 3. So this is how we represent a graph using a adjacency list representation. Each node has a list and that list has all the nodes which are connected to that particular node. And if this were a directed graph, then if these vertices, if these edges had directions, then the representation would change and we would say the list of 1 only contains the nodes to which there is an edge starting from 1. So 1 has one edge which starts from 1 and goes to 4. So 1 is going to have 4, then 2 has two edges which start from 2 and they go to 1 and 3, 1 and 3, and 3 has one edge that starts from 3 and goes to 4. So 4 and 4 does not have any edge which start from 4. So this is like empty. And that is cool. Shit, you sent a link, but it got retracted, and I like looked up how to allow links to be sent in the chat, but yeah, I don't know, something happened with it. Yeah, it got messed up. I don't know why people are unable to send a link. And that is adjacency list representation. That is nice. The constant n, this is the chosen so that all adjacency lists can be stored. For example, the graph, this can be stored as this. If we are talking in C++, and we do talk in C++. If the graph is undirected, it can be stored in a similar way. And for weighted, we can have, yeah, we can have edges like this. The first value could be the node which the ith node is connected to, and the second value could be the weight, like this. 1 is connected to 2 with a weight of 5, 2 is connected to 3 with a weight of 7, 2 is connected to 4 with a weight of 6, and 4 is connected to 3 is connected to 4 with a weight of 5, and like that. And this is also directed. That is why we have 1 connected to 2, but 2 not connected to 1. This shows that this is directed. No, I do not solve elite code contests. I don't even know how to participate in them. I mean, you do not have to go to all the places at once. The main thing is, if like for me, I think that if I become really good at code forces, and yes, if I become really good at code forces, then after a while, when I am good, I will be able to go to at coder and crush, yes, crush I think is the right word, not crush like this, but I will be able to become really good and increase my rating very quickly if I go to add coders after I become really good at code forces. So I do not have to jump around all over the place right now. Right now I can just become better and go later any place I want. The benefit of using adjacency list is that we efficiently find the nodes to which we can move from a given node through an edge. For example, the following loop goes through all the nodes to which we can move from node S. Auto U is the node that S node is connected to. Or we can go to all the U nodes if we are currently at node S. Adjacency matrix representation, this is very inefficient. This is a matrix who rectangular matrix where the side is the number of nodes, and if two nodes are connected then there is a 1, and if they are not connected then there is a 0, and if these are like directed here we have a directed edge from 1 to 2, then 1 to 2, there is 1. But from 2 to 1, there is no 1. It is 0. And also, if this was weighted, instead of ones and zeros, you would have the weight. And 0 would still represent no edge at all. Or you could think of it as they are connected, but the weight is 0. Now that would mess things up. So yeah, 0 would represent no edge at all, where each value adj a, b indicates whether the graph contains an edge from node A to B. Yes, and this is directed. The first one is the source and the second one B here is the target. If the edge is included in the graph, then AB equals 1, and otherwise if it is not included, then AB, adj, AB equals 0. For example, this graph is represented like this. And if the things were weighted, then instead of ones and zeros, we have their weights, which is true. The drawback of the adjacency matrix representation is that the matrix contains n square elements and usually most of them are 0. Yes. So this is taking much more space than we need to take. For this reason, the representation cannot be used if the graph is large because the size grows exponentially, like at literally exponentially. An edge list representation. An edge list contains all edges of a graph in some order. Okay, shit, yes. Now our representation is one-dimensional and we represent a edge by a pair and we have all of those pairs in a singular vector in one dimension. Or you could think of this as a matrix of two columns and a lot of rows, and the number of rows is equal to the number of edges. This is convenient. This is a convenient way to represent a graph if the algorithm processes all the edges of the graphs and then is not needed to find edges that start at a given node. Yeah, yeah, this representation would be required in some cases. This would be more convenient. This is a convenient way to represent a graph if the algorithm processes all nodes of the graph. If the algorithm processes all nodes at the graph in the graph and is not needed to find edges that start at a given node. Yes, that makes sense. Makes sense. This is convenient when we do not want to find edges which start at a given um, edges which start at a given node, but we just want to process the edges in some or any particular order, in any specific or any arbitrary order. That is when we use this representation, where each pair AB denotes there is a edge from A to B, and this is directional. The first one, the first integer is the source node, and the second integer here is the target node. So this is directional. This can be represented as a list. If the graph is weighted, then the structure can be extended to use a tuple, 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 where the first one could be, yeah, A, B, from A to B with the weight W. That makes sense. And that is the end of the first chapter. That is nice. So now there is only one chapter left for target, like today's target was 2 chapters. So only one chapter is left, and then we will do some CSES questions, and that is going to be nice. I have done some CSES questions of graphs in the past. By past, I mean like maybe a month ago at this point. And yes, I will do all of these again, and we will try to get this one right. I got this wrong the first time I did this. And yes, shit, yes, I do remember this one. And this was crazy. Look at this. Look at this. I tried hard to get this right. Yes, this was more than a month ago. This was more than a month ago. 8th August 2021. Not 2021, 21 August 2025. And I hope my phone is charging. It is charging, so that is nice. Ad coder contest. Ad coder has begun ABC. Really good. And there's ones next week. But, like okay, I can do ad coders contest, but now I'm just focusing on improving. And I think if I want to improve, I can just go to any platform. Wait, shit, this guy has a YouTube channel. That is crazy. I can go to any platform and just improve. And when I'm good at code forces, I can go to ad coders or top coders anywhere and increase my rating. That is nice. And this guy has a website that is has a YouTube channel. That is nice. I have seen him. He has done some things. He's from Iran, Tehran, capital. He has some blogs. Shit, this is one of his blogs. Video tutorial for Code Forces 1054 Iran. Shit, that is a graph. Okay, that is nice. That is nice. Back to topic. He has a YouTube channel, Algorithmy Academy. Nim Game, Part 2, Nim Game. Nim Game is nice. Nim Game is nice. Nim Game is also there in CPHP in game theory section. Yes, Nim Game. And now graph traversal and then CSES questions for the day. And it is going to be cool. And maybe we will even do one of the shortest path algorithms. Hopefully, let's see. There are only two traversal methods here, this chapter, or shit, or what we can instead do after this is go to CLRS. Shit, we can take CLRS side by side. That would be nice. We can go through CLRS side by side. So we can like we don't have to compare the writing we do not have to compare the writing styles. First we will go through graph traversal from here, then we will solve CSES questions, and then we will go through graph traversal. Shit, where is graph? Here. Representation. Okay, we will see what representation of graphs is according to CLRS, then breadth, BFS and DFS. And topological sort is something that I do not know about. I know like conceptually what it is, but how do we do it? That is a crazy thing. And it's going to be nice. And yes, that would be the challenge to get topological sort today. That would be cool. That would actually be cool if I did topological sort today. This chapter discusses two fundamental graph traversal graph algorithms, DFS and BFS. Both algorithms are given a starting node in the graph and they visit all nodes that can be reached from the starting node. The difference in the algorithms is the order in which they visit the nodes. DFS is a straightforward graph traversal technique. The algorithm begins at a starting node and processes all other nodes that are reachable from the starting node using the edges of the graphs. Yes, in a adjacency list representation, in some older compilers, the function make tuple must be used instead of braces, like this instead of this. Older compilers, this book came out in 2018. Example, let us consider how DFS approaches this one. So yeah, if you begin from a node, you first go to this thing, then you go to one of these nodes, which you go to like here, and then you go to here, and then you go to 4. That is, the search first proceeds to node 2. After this, nodes 3 and 5 will be visited. The neighbors of node 5 are 2 and 3, but the search has already visited both of them, so it is time to return to the previous nodes. And also the neighbors of node 3 Uh, Neighbors of node 3 are 2 and 5, which are visited. 5 is visited. That is nice. And then the only non-visited neighbor of 1 is 4. So we go to 4. After this, the search terminates because it has visited all the nodes. Yes. The time complexity of DFS is n plus m because we go to one edge, one node every time, and also we are going through every edge one time. We didn't go through this edge, but this is big O, not like exactly we go through every edge, but sort of we go through every edge, where n is the number of nodes and m is the number of edges because the algorithm processes each node and edge once. Implementation, we will not look at the implementation because we know the implementation and we will just do the questions after this. And BFS, breadth first search, BFS visits the nodes in increasing order of their distance from the starting point. Yes. Thus, we can calculate the distance from the starting node to all the other nodes using BFS. This is good for calculating distance, but this is also good for calculating DFS is also good for calculating distances. And yes, shit, this BFS being good for calculating distances does not mean that DFS is bad for calculating distances. Both can be used for calculating distances. Thus, we can calculate the distance from the starting node, that is the case, to all other nodes using BFS search. However, BFS search is more difficult to implement, relatively speaking, more difficult to implement than DFS. Breadth first search goes through, and one thing I have to see here is, yes, it is recursive. It is recursive. How would it be non-recursive? I think it won't be non. There might be some way to write BFS and DFS non-recursively. That would be cool to look up. BFS search goes through the nodes one level after another. First, the search explores the nodes whose distance from the starting node is 1, then the nodes whose distance is 2, and so on. And the distance that we get for, like when we say the distance is 1 and distance is 2, this is relative to the starting node. That is a subtle distinction. Like, of course, yes. The process continues until all nodes have been visited. Yes. Example, let us consider here and our starting node. Suppose that the search begins at node 1. If the search begins at node 1, we first go to node 2 and 4, which have a distance of 1 each from the starting node. Then we go to node 3 and 5, which have distances of 2 from the starting node. And then we go to 6. See, we go to 3 and 5, and then at end, we go to 6, and then our search is finished. And we have also filled this thing. Now we have calculated the distances from the starting node to all the nodes of the graph. The distances are as follows. Yes. Like in DFS search, the time complexity is same as n plus n. And implementation, we will not delve into the implementation because we will be solving questions very shortly, and that would be it for our implementation. Using the graph traversal algorithms, we can check many properties of graphs. We can check many properties of graphs. What are the properties? Like, is the graph a tree? Is there a cycle in the graph? Or, yeah, is there a cycle in the graph? That is one thing we can check. And the distances are not properties. They are just facts about the graph, not the properties, I think. And usually both DFS and BFS search may be used. Okay, that is a nice thing to state, that usually whenever we want to check some property, then we can use any method we want, DFS or BFS, usually. But in practice, DFS search is a better choice. DFS is a better choice because it is simpler to implement. In the following applications, we will assume that the graph is undirected. Okay, and these are the properties that we can check for connectivity check. Finding cycles, yes, finding cycles. Bipartiteness, those are the only things, three things we can check. Connectivity check. Are there components? Yes. So when we can check for connectivity by starting our search from a particular node and going through all the possible edges, which are with all the possible nodes that we can go to from our search node. And still after that, if we have some nodes which are unvisited, then the graph has components, and we can calculate the number of components whenever we see a node that is not visited. We apply the DFS algorithm, go to all the nodes which could be reached from this current node, and increment our counter by 1 whenever we see a node that is not visited. And then we keep moving forward, and if we see another node which is not connected to anything, then we increase our component counter by 1 again and call DFS algorithm on that node. For example, here we will start going through node 1 and till 5. When we see node 1, we see that node 1 is not visited because we just started our algorithm. We will increment our component counter by 1, which was initially 0, so now it is 1, and we will call DFS on 1, and that would make node number 3 and 4 visited. Then, since we are going iterating by 1, after node 1 we go to node 2 and we see that node 2 is not visited. We increment our component counter by 1, and now the component counter is 1 plus 1, which is 2, and we call DFS on node 2, and now 2 and 3 are also visited. Then we go to node 3 and we see it is visited, so fine, we do not do anything. 4 is also visited, 5 is also visited, and at the end when we come out, our component counter is 2, so therefore we have two components which we actually do have. So that is cool. DFS starts from node 1 with its these things, and still we have two things which are not visited. Since the search does not visit all the nodes, we can conclude that the graph is not connected. In a similar way, we can also find all connected components of a graph by iterating through the nodes and always starting a new DFS search if the current node does not belong to any components yet. And that is literally what I just said. Now, finding cycles. While using a DFS algorithm, if we ever reach a node which has been visited before, but it is not the node which called the DFS for the current node, then there is a cycle. A graph contains a cycle if during a graph traversal we find a node whose neighbor other than the previous node in the current path. Yes, other than the previous node in the current path, that is something we have to keep in mind, has already been visited. So if we start from 1, let's say we go to 3, and then let's say we go to 4, and then after 4 we see we can go to 3 and to 1. 3 we will not go to 3 because we just came from 3, and we will go to 1, but 1 has already been visited and 1 is not the previous node in the current path. Therefore there is a cycle in this node, in this graph, and there are two cycles, 1 3 and 4 and 2 3 and 5. This graph contains two cycles, and we can find one of them as follows. We go to 1, then to 3, then to 2, then to 5, and when we are at 5 we see we can now go to 3, but 3 is already visited. So there is a cycle here. After moving from node 2 to node 5, we notice that the neighbor 3 of node 5 has already been visited. Thus the graph contains a cycle that goes through node 3, for example this. So yeah, yes, and we can use some state storing mechanism through which we will be able to find the exact cycle path like this. And that would be crazy to find the exact path which is creating a cycle. That would be cool. Another way to find out whether a graph contains a cycle is simply to calculate the number of nodes and edges in every component. The number of nodes and edges in every component. If a component contains C nodes and no cycle, then it must contain exactly n minus 1 edges. So it has to be a tree. If there are C or more edges, the component surely has a tree, has a cycle, which is the same thing that we saw earlier in trees. Here, wait, where is trees? Tree, yes. A tree of n nodes has n minus 1 edges, and if the number of edges is lower than n minus 1, then it is a graph with disconnected components. And if the number of edges is the number of nodes or greater than that, then there is going to be a cycle, at least one cycle. Okay. Now bipartite checkness. But this thing is like pretty cool. How I'm thinking about how what information we would we have to store to find out the exact path which is creating a cycle. And we will be able to do something with it because we know where our what our starting and ending point is. Right? We do know what our starting and ending point is, and while we were traversing, we would store all we would store where we are going next, but that is just what adjacency list stores, so that is redundancy. But if we do know that our path, our cycle begins and ends at a certain node, which is 3 in this case, then how would we be able to find out the cycle, the exact path for the cycle? There might be a string. We can start looking from 3, and from 3 we can go to 1 to 4 to 2 to 5, and our DFS function will return true if there is a cycle. It will return a boolean value and a string if there is a cycle on that node. And how will it know if there is a cycle? It will know if 3 is being visited again from that node, and that share. But then the DFS algorithm would also need to know what the end node is. Yeah, it will be fine. It will be like implemented. There would be some way to find the exact path which is creating a cycle. Yeah. Bipartiteness check. The graph is bipartite if its nodes can be colored using two colors so that there are no adjacent nodes with the same color. If we can color a graph with using just two colors, and also no adjacent nodes have the same color, then the graph is a bipartite graph. It is surprisingly easy to check if a graph is bipartite using graph traversal algorithms. Okay, the idea is to color the starting node blue, all its neighbor red, all its neighbors blue, and so on. If at some point of the search we notice that two adjacent nodes have the same color, this means that the graph is not a bipartite graph. Otherwise, the graph is a bipartite graph and one coloring has been found. Okay. For example, the graph this is not bipartite because we begin from 1 and we color 2 as red, then we color 3 as green, and we color like this is some sort of some color. We notice the color or both nodes 2 and 5 is red. Okay, this is red. It is because of the dark reader extension, dark mode reader extension, which is making this changing this from red to this color while they are adjacent nodes in the graph. Thus, the graph is not a bipartite graph. This algorithm always works because when there are only two colors available, the color of the starting node is in a component. It determines the colors of all the other nodes in the component. It does not make any difference whether the starting node is red or blue. It is just inverting all the colors. Note that in general case, it is difficult to find out if the nodes in a graph can be colored using key colors. Shit, it is supposed to be NP hard using key colors so that no adjacent nodes have the same color. Even when k equals 3, no efficient algorithm has been found, and the problem is also NP hard. And with that, we can move on to the CSES questions, which is like more tangible thing to do. Bro, I'm new. Can you tell me what you are doing and what primary language you use? I use C++ primarily, and also the main goal, I would say, for the channel is to show you that you can learn and you can become as good as you want at any arbitrary thing. You can just pick anything you want. You do not have to be born in a certain way to be good at something. Born like talent only matters at maybe the highest level of competition, like for world championship, but we are not competing there. And before that, it is up to hard work. You can become really strong. And I want to show that. No, I do not teach. I do not teach. No, I don't know enough to teach anything. The main goal is to just show you that the main goal is to be unfiltered. You can see I began doing competitive programming for the first time 3 months ago, and I have grown immensely. Not as much as I would like, but I have grown, and it is out there for you to see. And you can see if I have grown, then you can also grow at any arbitrary thing you want. And maybe you will be able to realize about yourself that you can become good at anything you want, but you have to be willing to be putting in the hours and be consistent daily, and yeah, put in conscious effort. Deliberate practice is the term. And now counting problems, counting rooms, graphs. Yes, yeah, I did this for the first time last month, and yeah, this is going to be cool. Let's go. CSES questions, and then maybe we will go and read some CLRS. Yeah, CLRS, graph algorithms. It is going to be pretty cool. And right now we do this CSES. Thanks. My last question is, I have learned C++ basic. The learning part was fun, but now I'm confused and very tired what to do next. Okay, basic part. Do you mean, do you understand what what is happening under the hood? What is like literally happening under the hood in CSS, CPP? Like what are streams? What are buffers for IO streams, and the fact that IO streams and standard IO printf and scanf functions, they have different buffers which are by default synced with each other. And if you need to know like basic internal knowledge about C++, you can use the C++ programming language, this book, C++ programming language. This is just the material, but you can grow from any place you want. But learning part was fun, but now I am confused, and that is very normal because C++ is one of the hardest languages, most difficult languages out there. template, OPP, etc. These types are cleared. Okay, these are cleared, so that is fine. I think you can, if these things are cleared, what have you written in C++? You can go to advent of code and write some simple programs which solve problems. And if you want to like refine more your C++, then you can go to build your own X and write something. You can go to this GitHub page, build your own X by codecrafters.io and look for C++, and you can build your own 3D renderer in C++ or your ray casting engine or your own Redis in C++ or a emulator virtual machine in C++, and that would refine your C++ quite a bit. Yeah, that is what you can do now. And for us, let's do CSES questions. And wait a minute, just 10 seconds, 5 seconds or 10 seconds, I'll be right back. Yes, I'm right back. Yep, you're welcome. I mean, Build Your Own X is a pretty cool website. I'm planning to build after competitive programming my own Redis, and that would be very cool because we will be writing about protocols and ICPC client connections, database things, and it is going to be pretty cool. And now, enough yapping. Tmux. CSES, CD, graphs, and let me actually RF graphs and make it start new vim. Exit, and cool, we will do this question now. Okay, what even is the question? You are given a map of a building and your task is to count the number of its rooms. The size of the map is n into m squares and each square is either a floor or a wall. You can walk up, left, right, up, down through the square floors. The first input line has the integers n and m, n and m 1000 at maximum, the height and width of the map. Then there are n lines of m characters. N lines, n is the number of rows and m is the number of columns describing the map. Each character is either a floor, which is represented by a dot, and a dot, which is represented by a wall like this. So yeah, we can just take in this whole state, and we can start traversing from top, and whenever we see a dot, we will call our DFS algorithm, and our DFS algorithm will have two choices at every floor, either top, left, bottom, right, and it will change the current one first of all to not visited or visited by literally changing the graph from a dot to a hash, and it will call DFS on the next place wherever it can go. And also we will have to keep in mind the bounds. We do not want to be going out of bounds of the graph or the floor. NM, and we will have a vector or string. We'll call it graph. Just G is fine. The number of rows is n, and the number of columns is going to be there. Like, yeah, for n I plus plus CNGI. We have the thing, and now we will start reversing, and I equals 0, I less than ni plus plus, and for int j equals 0, j less than m and j plus plus, and if the current one, if g I j equals a dot, then we, okay, and this is very equivalent to finding the number of components, which is like, okay, cool, makes sense. We'll have int answer equals 0, and whenever we see a not visited node, we will do answer plus plus, and we will call a dfs function on this particular place. We will give in the graph the ith coordinate and the jth coordinate, and that should work. And our graph dfs will not return anything, but it will take in a vector of string, a reference called g, int I, and int j. And what it will do, first of all, it will suppose that the particular cell on which the DFS has been called, it has been put as a visited node. So we will do gi j equals hash. So this is going to be considered as like visited, and we will also have a vector of pairs, not vector, we can have a simple array of pairs, pair in int, we will call it move, and it is going to have a few elements, and this is going to represent what the possible moves are. 0 1, this is equivalent to going to the right, the second number represents the column, so this is equivalent to going to the right, and 1 for going to the left, that is another move, and 1, no, this is not going to the left, this is going down one cell in cell, and this is 1, and then minus 1 0. Yep, this is going to the right, this is going down, this is going to the left, this is going up. And now for auto x comma y, x and y are moves. In move, what we will do is int ni is going to be I plus x, and int ny is going, nj is going to be I plus 1, j plus 1. Now, if they are in bounds, if I smaller than, if I greater than, first of all, yes, ni, we will check a few things. Ni has to be greater than or equal to 0, and ni has to be smaller than g dot size, because that is the number of rows. And for nj, nj has to be greater than or equal to 0, and nj has to be smaller than g first dot size, which is the number of columns. If that is true, and we also have that this thing is not visited, and like we can at this point do an I nj, and this is not going to give us error because we know that ni and nj are within bounds. This thing, this thing equals not visited or a floor, like some place where we can go, then we will change this to visited, which is indicated by a hash, a pound symbol, if you will, and call dfs on this thing, and I g ni nj. That should be enough. And then see out answer. Let's see. Hmm. Hmm. Move is ambiguous. That makes sense. Move is ambiguous because there is also a function std standard move with a capital with a small m. So we cannot use the name move. We will use some other name. Let's replace, substitute move with moves. How is that? That is the correct answer. That is nice. Let's submit. Submit. Choose file CSES, graphs, counting rooms, CPP20. Yes, let's go. Pending, pending, testing, testing. Okay, that is cool. That is cool. Now to labyrinth. This one you are given a map, and yes, I have done this before 1 month ago, but just refreshing the memories. You are given a map of a labyrinth, and your task is to find a path from start to end. You can walk left, right, up, down, and A represents in the input. We have two integers n and m, just like the last one, with a okay. Okay, this is good. Then there are n lines of m characters. Each character is a floor, a place where we can walk, a pound, a wall where we cannot walk, A, start, B, and there is exactly one A and one B in the input. Print first yes if there is a path. There might not be a path at all. If there is a path, print the la print the left print the length of the shortest such path. So we will be using BFS, and its description as a string consisting of characters L, R, U, and D. You can print any valid solution. Okay, and the answer has to start from A, and it will say, how do we go to B? This is much better than the last one. Okay, we will be using BFS here. And N, M, and a vector of a string G size N for int I equals 0, I less than N, I plus plus, seeing VI, and A, int I, comma J, and yes, equals 0 mutually for int I is already equal to 0. I equals I less than N and I plus plus. Here we are looking for A, and J equals 0, J less than M, and J plus plus. If Gi J equals A, then we break go to. We are not supposed to use go to, but no is supposed to use go to somehow. Bool F as in like found, false, and if this is the case, then break, and here if break, and when we are here, we will know I and J. G, I, J will be the index for the starting point, and from there we have to go till the end point, which is going to use BFS. So we will have a queue of the next a queue of pairs, queue of pair of integers. Yes, and we will call it queue, and we will have q dot insert. I think it uses push, the word push, q dot push I comma j. push and I comma j, and now we have to find the shortest path from A to B. From A to B. So we will run while not q dot empty, but yes, we have nodes, so we'll need some two-dimensional. How do we store the path? That is the same the thing, right? How do you store the path? Or do we have a matrix of strings? That is bad. We do not have a matrix of strings. We will have a matrix of characters. Yes, we will have a matrix of characters. That makes sense. And whenever we are going from a certain cell, for example, if I'm here and I can go right, whenever I make a move to left, right, or any place, I will go to the matrix location of that thing and I will put R to this thing because I moved from here right. To get to this point, I had to use R, right. And then I will know the location of B, and B would have U. And I will like go in reverse from B to A. Yes, I will go in reverse from B to A to get to A. Yes, makes sense. So here we will have a of vector of characters. We will call this P as in path with n rows, and vectors are m vertices. And initially everything is equal to hash. Let's let's say that. But for A, initially we'll have to specify something for A. When yes, at this point we do know where A is. So here we will say P I J equals dot. A is dot, but everything else is a pound. Now we will like to have array, a static array of moves, and the moves are again 0, 1, and 1, 0, and -1, 0, and 0, -1. And here we will have the top removed. Auto x comma y equals q dot top and q dot pop. We remove the top, and yes, we remove the top, and we will go through all the possible moves. So for auto autodidact, that is a nice term, autodidact. For auto dx, change in x, and auto dy in moves, we have int nx, new x is x plus dx, x plus change in x, and ny is new y is y plus change in y dy. And if this thing is in range and this is a place where we can go to, then we will push it into onto our queue. So we have to check a few things. Nx has to be greater than equal to 0, and nx has to be smaller than n. Yes, n and m has not been messed up with, so that is nice. And we have ny greater than equal to 0, and ny smaller than m. Yes, and it is a place where we can go to, right? That is cool. It is a place Okay, shit. If that is the case, here we will have to do Qij equals a hash. We are marking A as visited. And this place, G, Ni, Nj is a visitable place, some place where we can go to. Okay, shit. This is shit. We need to relate the moves. Hello. Basically, you know basics of DSA topics, even graphs. Now you are just polishing. Yes, yes. Yeah, basics. Basics, I know. Polishing any main topic is not foreign. Well, I can think whenever I see a like foreign topic, I can formulate what it it is trying to say and what it is about, and then I like check my theory with either ChatGPT or looking it up on the internet, and yeah, it is just hypothesizing and checking if I'm correct or not. And basics is like has different meanings for different people. Best way to solve CB31 sheet, you just start solving the sheet. That is the best way to solve. There is no like it is a sheet beginning from 800 level. You can just start solving the question. That is the best way. I don't know if and yes, okay, yes, shit. You start solving the sheet, and also side by side you do your research with this book, Competitive Programmer's Handbook. That is, I think, the best way. You are also solving questions and you are also doing your research, quote unquote. And the main thing is not to solve those questions, but the main thing is to have a model which you can apply to learn anything you want and not just getting good at competitive programming. Design a model and prepare a model to get good at things and learn. Learn how to research and not get good at competitive programming. Learning how to learn is the main thing here. And yes, shit, now there is a problem here. I have the move, but we don't know. Shit. Okay, what we can have is instead of a pair or a array, we can have a map. A map of character to pair, right? Yes, moves. And it will be shit, how do we initialize a pair? I think like this. How do we initialize a map? I think if I just say u and the value for u up is okay, what do I want u to be? Yeah, literally just up when something goes up. And I really want to check this this is the right way. For that, we have the LSP star blank D. Yes, that does seem to be correct. We do not have Q here. There is some error. QIJ, what is the problem? Okay, that makes sense. Should be G. Q dot top uh, is not a thing. Yes, Q dot front is a thing. Okay, and this is the right syntax, so that is cool. LSP stop. So for U, this is the symbol, and for down, we have 1 and 0, and then for right, we have 0 and 1, and then for left we have 0 minus 1. And now we will have to change this syntax, not this one a bit. Okay, this can be a bit more complicated. Can I do this? dy and here m, so that m will be the move, the character, and dx and dy will have the moves. And let's restart. Okay, we cannot do that. We cannot do that. Let's ask ChatGPT how to do this. Like you have done graph question before, now you are studying it again, right? So I mean, at least once you have gone through these topics. Yes, I've gone through these topics, but now I want to go through them uh, in like full guns blazing. And after this, I should be really good at graphs so that you can give me any problem from graphs and I should have at least an idea as to what I can do with that problem. So yeah, making it more official would be the term. Okay, let's ask a question. Okay, I have a map in C++, like map char pair int mp. How can I iterate through it using the unbinding syntax? Uh, Something like for auto m a comma b in mp. Yes, that is the thing. Auto ab, and then I can destruct ab here. Okay, okay. Why not directly? Because C++ structure binding doesn't yet allow nested destructuring. Okay, it is like not available in the language itself. That is fine. We can call this d and then auto dx and dy equals b. LSP restart. Yes, there are no errors except at that point. Use of undeclared identifiers. Okay, because it is nx and ny. LSP how to repeat the last command in NV. Oh, last X command using this add this add. Okay, that does work. Executing the last X command. Yep. And now we have to create a path. So at this point, we know that we can go to NX and NY. So we will update the location. So P, N, X, and N, NY. We are saying we got to NX and NY. What was our move? Our move was M to get there. And now we have to say that this is visited. We will say that by making it a wall. And we can put this into our queue. Q dot put push put push q dot push n, x, and y. And also, shit, if this thing is not a hash, because it could be B. So here, before this, we will check bool done equals false initially, and if ever we see that g, nx, and ny is B, the endpoint, then put done equals true first, put this in the path, how we got to this place, and do this, and also we will have I and j will store the index for the B. I equals nx and j equals ny. And we will break while not empty and not done. So when we get out, if not done still, then see out. No, we cannot do this. Else we can do this somehow. And now we have to find the path. We have to reconstruct the path, and I and j have the indices for B. We just have to go back beginning from B, and this is going to be a bit tough. U, if we have U, then we have to go down, because at the end, if our initial thing was like this, so that is too small. If initially we had something like this, then like this doesn't even look good because the dot is very small. Right. If we had initially something like this, then our eventual path is going to look like this. This will be L, this will be D, this will be D, this will be R, 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 this will be up. And what we have to return with this is L, D, D, 1, 2, 3, 4, 5, U. And that is the answer. Yes, L, D, D, 5 R's, and then U. So whenever we see a U, we have to go down. Whenever we see a right, we have to go left, left, left. Whenever we see a D, we have to go up. And whenever we see a L, we have to go up. Which we can do, we can have a different map of characters, and we can also turn off our LSP stop map of characters. It will have moves. Back, it will be called back. Whenever we see a U, it means we, to get to this place, we had to go up, which means now to get to that cell from which we got here, we have to go down, and down is this. And yes, way down we go. And whenever we see a D, we have to go up. Up is -1, 0. And whenever we see a right, we have to go left. Left is 0, -1. And whenever we see a L, we have to go right, which is 1. Correct, correct, correct. Yeah, pretty cool. Delete, delete, delete. Okay. And also we made in this P thing A equals a dot, or we can make it A, literally A. So that is fine. And string answer initially empty. And while P I J is not equal to A, is not equal to like literal A. So if this is not equal to A, then answer plus equals whatever is at that location P I J. And now we have to update our IJs by auto di dj. Difference in I and j equals back P I J. And now we have to update I and j. I plus di, j plus equals dj. And at the end, we will reverse our answer begin and answer dot end, because we started looking at the path from B, and then we will see out first of all answer dot size, and then I guess on the second line, yes, on the second line, we will output answer with a brand new line. And hopefully this works and does not break, but it does break. Yes, at the very end, I messed up. This has to be a S. Okay, application out of bounds error. Hi. Do we see a high? We do not see a high, so we got out of bounds way before this. We do not see a high even there. Wait, shit, we should have seen a high by then, but we didn't. Okay, there is some error. And when to see the solution and editorials, when you know for a fact that you will not be able to find out the solution on your own. And yeah, it is good to look at the editorials because the main point is to learn. And also I would recommend that you watch this video. Need code, lead code, improve video, or I think this is the one. This is the one. Yeah, and this video is very good. This video is very good. You should watch this one. And also, I think this one. And you can watch these two videos. In one of these videos, he says that whatever problem you see, you do not have to implement an algorithm every time that you see a problem. That is not the main thing, because you won't be able to, you do not have to discover a new algorithm every time you see a problem. So you do not have to discover Dijkstra's algorithm. You can just look it up. And also there is a Primogen's video on the same thing. Uh, Neat code. W take. Yes, this is the W take. Neat code's hot W take. Yeah, this is the video. You can watch this one. This one is also pretty cool. 35 minutes. Yes, 35 minutes. But yeah, it is pretty cool. Let's hop on Discord server after you end the stream. Okay, yeah, that would be fine. I have to do some muscle ups, but yeah, okay, we can do that for a while. After we are done with the stream, how long has it been? It has been 2 hours and 25 minutes. We will go for at least 3 hours. Yes. Okay. And end line is not, W is not being printed, so there is some mistake. Done false, done true, if done. Ah, shit. If done, then break. That was the thing? No, that was not the thing. Wait, what? Equal to M? Yes, M makes sense. Done equals true. I, J, N, Y, N, Y, yeah, N, Y, New York. Q, insert into Q. Just random things. Even though the not operator has a higher precedence. And Pij equals A and Gij equals 0. And yes, F equals false. Okay, F equals and true. Are we getting till this line? Okay, we are even getting the right answer. That is pretty cool. Okay, that is nice. And I would like to go to the washroom. When you yes, here. I mean, I break when I find ing, and also these are defined outside, so pretty cool. And now this thing, and yes, I want to ask you something. Here I'm using this thing because I need to know ULDR and also what are the moves. So is this like nice, or is there some other better way to do this? Already broke? I am broke. I broke. Is this the right way? I think there might be some other better way to do this. When I am going to a cell, I see which move is making me go to that cell, and I have a path matrix in which I am putting these characters ULDR when I go to the next cell. And when I'm tracing back my path from R, I have to go to the opposite direction of whatever the current character is in the path. So if I got to the current cell using U, using a up move from the last cell, then I have to go down, and to go down, this is the move I have to make. Is that like right? Storing reverse direct, just subtract the move. Shit. Okay, that is genius. Directions map is good. Okay, shit. Okay, that is pretty cool. That is pretty cool. Shit. Yes, I can subtract the move. Back, not back, but move. And here we can subtract. Hmm. Shit, that was good. That is good. That is good. That is good. That is good. Yes, that is good. And is there any other inefficiency? I have this. Uh, I must use two matrices, one for the grid and one, and I'm not using a visited matrix. I am putting every, I'm replacing every dot by a hash so that I won't go there again. That is like changing the input which was given to me, but here we do not need the input later, so I think this is fine here. Okay, yes, we can do that. We can do that after the stream for a while. And let's like submit this and see how this is. Labyrinth. And this was pretty cool. We can subtract the direction instead of storing the back. Okay, runtime error, runtime error. Runtime error. What is the error? Can I see the error? Runtime error. Am I indexing something outside? And you did say I already broke. You can do it in place by replacing grid. Yo, hello. How are you? By replacing grid cells with the directions themselves. Ah, shit. I can reduce the state even less. I can use like half the memory that I'm using. That, yes, we can do that. We can do that. We can do that. This would just be A so that I know I am at the starting position. Push, okay. And instead of path, we'll change G and we will have to check if the next thing is a dot or if this is okay. I just changed it. It was not wrong before. Okay. This or G and X and Y equals B. Like any one of that. Hmm. Hmm. Put this in. We are doing done equals true. Take. If not done, then see out no. If done, then see out yes. And then we will calculate, find the answer. Miami for a holiday. Okay, you are roaming quite a bit and you are also doing your lead code questions. It is over 310, 18 something. Stiff droid. That is pretty cool. And here, when looking for the path, G, G, answer plus equals. Yes, because it has the character. G has the character. Okay, cool. Hmm. So we have optimized two things. First of all, we are not storing any map for backward relation because we can just subtract the direction and also the grid. We do not have two grids. So shit, we are the single matrix is has the original matrix that we got also is performing as the visited matrix as the like visited nodes and also for finding path at the end. That is some uh, superposition quantum gravity thing. But still, this is giving us error, so something is wrong. Labyrinth 309. Okay, my bad. Okay, wrong answer. Wrong answer. And yes, I just want to point something out that answer equals answer plus gij. This is less efficient and this one is more efficient because here this thing creates a new temporary R value string and that is called with a move operator onto this answer string. So here this is like this is going to give us TLE, time limited exceeded error, if we have if we are appending a lot of characters, and this thing is not going to give us any error. This is the same as putting some value, like calling pushback on a vector, but this thing is like creating a new vector, adding this new element and copying that or moving that vector onto the place where answer is. So that is like a lot more work than we have to do. My dad got a holiday due to anniversary, so yeah, partying. That is pretty cool. Miami, where even is Miami? Miami, Florida. US state of Florida. It is the second most populous city in Florida with a population of this much. A founded by Julia, Mrs. Julia Tootle, Toot. And Florida is there, Miami is there, and shit, there are a lot of roads, but here there is just farms, I guess. Farms, hills, or stuff like that. A pretty nice place to roam around. Miami is cool. Yes, seems like cool. It is surrounded with water. And shit, you are still awake there. And it is very early for you. That is how you do things, I guess. But something is wrong. Wrong answer. And I do not like want to look at the problem statement which gave the wrong answer. That is what Eric suggested. So we will go with that. We'll just look at the code because during a contest we cannot look at the problem statements which gave us the wrong answer. It just says wrong and nothing else and no other clue. It just says wrong. While not empty and not done. So if I ever get done or if this thing becomes empty, we go out. That is nice. Let me go to the washroom. I'll be like right back. Explore some haunted areas. Shit. At a cool place. I know I'm cool, but seems fun and spooky at the same time. Yes. Go explore some haunted areas. Like it would be fun. Haunted places are like pretty cool. Your monkey brains start working. You know logically that there is no one there sitting on the chair in the corner, but your monkey brain goes danger, 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 run, even though you know there is no one. And is something wrong with these? Up is -1, down is +1, right is +1, left is -1. Cool. When we take in the strings, then we take in the strings. Then in this section, we find A, where A is, and why are we putting A equal to A? That is pretty cool, crazy, fine, don't have to do this. We declare the queue, we push back the coordinates for A onto the queue, and we say done equals false. And yes, what are the invariances in this loop? In the loop, the invariances is that whatever the top thing is or whatever is in the queue, it is already marked as visited and its path is also updated. And we only have queue at the beginning, which is marked as visited, and the path is updated. We do not come from any place, we just go to it. And this also is fine, even if A and B are side by side, this is going to work. If the size is 1/2 and we have A, B, answer should be R. Yes, R. We just move right. And if 2/2 and this looks like dot B. Yes, down and then right. Cool. So that is working. YouTube is blocking my comment. Lol. Shit, what did you comment? There is no monitor. Okay, my bad. Monitoring. Welcome to live chat. Remember to guard your privacy and abide by community guidelines. Okay, be within the guidelines. There is a house where having really horrifying backstory and it looks so spooky at night. Go there. It is night right there. I guess yes, it is night there. So like early in the morning, you can go there. I guess it is going to be fun and shit, it is also going to be scary and dangerous. Shit, w- hobos, or what are they called? Hobos? What is uh hobo? No, that is not the thing. Hobo or homeless people. So shit, no. Yeah, there was some term for describing people who could be dangerous and lurking at those places. Completely abandoned. Shit, we don't have a lot of abandoned houses near here, but it would be cool to explore them. And yeah, you should go and explore. It would be pretty cool. Next B. If done, then break. If not done, then output no. And we are also not updating I and J at any other point. Nope. I and J are pointing to the place where B is at. Okay, let's look at the state problem questions where we got the wrong answer. We said the stain still exists of red fluid. Red fluid. I wonder what that could be. Know what I mean? Yes, I know what you meant. even though chat is not moderated now. I know what you meant. Okay, correct output is yes. I said no. Here also I said no. Why am I saying no? Q dot push back n x and y. There's something wrong. If someone sees those red fluids on the wall, floors, etc., they're also exploring alone. It's stuffed up completely. Is that what you were trying to say when your comment got blocked? Those red stains on the walls and floors. Good. The haunted house, the cabin in the woods. Yep, crazy stuff. New x has to be less than n, and new y has to be less than m, and we can go there. That is, it is equal to a dot or equal to b. Now, if this new thing is equal to a b, then we do done equals true and go to next thing, and we break. And by this, we are updating the move to get to this place, and also we are saying that this thing is visited, so do not go there again. Yes, we can say that. And then we are putting this into the queue. Queue dot front done is false, done is true later. Equals m, and m is only equal to udrl. That is okay. See, I mean, but see, backstory where entire family was. Shit, the back, it has a backstory. Yes. Primogen is streaming right now from a tower. That and all of his day 1, day 2, day 3, it is currently day 5 or 6 right now, and it is pretty cool what he is doing. The prime major. Bool done equals false. We are not making done equals true. It is only becoming true at this line. Done equals true. Update the move. Update I and J, but we are not getting inside this thing somehow. Why? Are we taking the input correctly? I think we are at least taking the input correctly. That is fine. Is it? It is not because of that. A map n m vector of strings called G and strings initially empty. Then we take into string I n strings in total. Yes. Found is false. When found, we break. I less than n, m, j less than m. Find a. If we did find a, put f equals true and then break. And outer loop, we will see if f, then break. Now I and j have the coordinates for a, and q, we have a q here, q of integers I and j, and the maximum value that these integers can have is 1000. So integer is sufficient for holding these values, and we push onto the q I j, which is nice. And then we do bool done equals false, and while our queue is not empty and while we are not done, what we will do is we will get the top or front things from the queue, and we will pop that front thing from the queue, right? That is how we do it. Pop. Yes. Push and then pop and front to get the thing, and then we get moves, all the possible moves we can make from this current cell. And dx and dy, nx and ny are the new indices, or yeah, new indices for the places we can go to. And here, if nx is in the range and ny is also in the range, and we can go to g nx ny if it is equal to dot or if it is equal to b. Those are the only conditions. And if g nx and ny equals b, then done equals true. Update the value, update the way that we got to this point, update I and j and break. And since done is true, here we will also exit. When I do break here, do we also go here? Shit. I think not. Just in case, so that we do not perform these two statements. so that we do not execute these two statements. And anyways, done is true, and we are not ever making it equal to false again. And if done is false, then do this. Otherwise, why is this E of different color? Why is this E blue? And C out. Let's restart. And string. This is the answer. While current string is not equal to A, what we'll do is add this, however we got to this string, onto our answer and get the moves that we had to implement to get to this place and subtract those moves and go back in time. And yeah, we only go backwards. Let's submit this again. Hopefully it works this time. And it feels like we only go backwards. This is still not working, and somehow I was able to get this right last month. I feel like there is some little technical thing that I'm messing up. Done is false. Yes, done is false somehow. X, Y are the current coordinates. And here we are making our move in this section. Dx, dy, we deconstruct the move using auto unbinding. Dx, dy equals d. And new x, new y are all is also correct. And x great n x is in the limit, and y and y is also in the limit. Yes, nx is in the limit, and ny is also in the limit. And this place in G, we can actually go to this place in G. That is good. And if the next place is equal to B, like literally equal to B, there's a mistake in not being able to find B. Though it does work here. We do output yes and all the correct things. So I don't know. I don't know. There's something wrong with this. There is some diagnostics required. And okay, it is correct here when 10, size is 10, size is 10. Okay, here also size was 1000 and we did got the correct answer, but it was no, so yeah. And here we said no when the size was 1000, when the size was 1000, no, 1000, and we said no, 1000, we said no. And when the size was 1003, we said yes, why not? And when the size was 3000, we said no, of course not. Wait, maybe our right move is messed up. Is our no, moves are correct. U is -0, that is correct. And D is +1 and 0, and R is 0, 1, and L is 0, -1. All of these are correct. UDLR, UDLR. I think we can also do Q dot erase, like fine. This will exit anyway. And shit, if we are doing that, then we don't even have to do done. No, we do have to do done. But we don't have to do check done here. Because Q is becoming empty. Okay, erase is not a function. I guess it is clear. Not Clara, clear. Clear is also not a function. How to be a Q in C++? Clear, empty, pop. While not empty, pop everything. Is that efficient? While not empty, Q dot. We don't, that is not very efficient. But this is going to work. Yeah, this is going to work. And not done. We'll say done equals true, and here if done break. Okay, we don't have to check if done break because we are checking done here. That does not work. That does not work. That is not working. And I do want to get this right. I guess, yeah, I will get at this question at some later point, and I have already streamed for 3 hours, so that would be enough for today. That would be enough. That would be enough for today. And how do you use test case thing? Yeah, I know it's a plugin. And yes, so for we need two things. One thing on the browser side, which is this extension. We need this extension on the browser side, and on the Vim side. Okay, yes, I'll be there. Bro was sitting right there. Yes, I'll be there. On pressing leader A. Okay, leader A, I think, is the default for assistant new Vim, but I have changed the default. Let me show you. I changed the default to leader CPP because I use leader A for harpoon, which is this leader A. Yeah, you can change the default to whatever you want. So I use leader PPP, leader CPP, PPP, and that is nice. That like does work, and that is advertisement by Brave for Proton Mail. Yep, and does it auto check? Auto check? No, no, no. Uh, it does not. When I'm here and I press CPP, I have to press R. It compiles and checks. Compiles and checks. And the folder structure is like this. If my file is here, then it has a different directory, a hidden directory .est for assistant, and all the things are there in JSON format, the test cases, and then it also compiles in the same folder and like checks for them how they are. And we can also change that. These are the arguments: file name, compiled with optimization. No, should this is for O output, and output should be the file name without extension. You can change that if you want, and that is just the power. Yep, JSON. And for today, this would be the end of today's stream. And thank you for being here. I simply will push the compilation to /tmp. So that it goes away, the binary goes away later. Okay, shit. And whatever you put in the /tmp folder, does it get deleted after a while? /tmp as in like temporary, I suppose. And shit, you were unable to see the screen. Yes, I will be joining the DC. Let me see. Okay, there is some stuff here. Default equals question mark. /tmp. Some folder listeners. Shit, is this some like secret ID which you have seen? It also keeps the directory structure safe. Okay, I will look it up. TMP and okay, directory structure TMP. Yeah, I'll look it up. And this finally would be the end of today's stream. Just 3 hours, and I was unable to do this labyrinth question. Anyways, and thank you for being here. Actually, and bye.